We have been talking about random variate generation, and today we'll start by reminding what it is and what we've done so far, and then I'm going to actually do an example by hand by request, and then I'm going to talk about the composition method, and then we'll look at it in SimKit. So as a reminder, random variate generation is about taking independent, identically distributed, uniform 0-1 random variates and produce a sequence of independent, identically distributed random variates that have a given cumulative distribution function, or CDF. And the method that we have presented so far is the inverse transform method. That is, if we have a uniform 0-1 random variable, which we assume we have, then what we do is we apply the functional inverse of the CDF to that uniform, and that whole quantity has the desired CDF, as it turns out. Okay, so now I was requested to give more of an example, and so that's what I'm going to do now with my doppelganger, who's going to share a whiteboard. Okay, so what I'm going to demonstrate this with is the Weibull distribution. And the Weibull distribution has the following cumulative distribution function. It is the functional form is 1 minus e to the minus x over lambda to the k. And that's for x bigger than 0 and 0 for x less than 0. Okay, and this is actually it's a very interesting and very useful distribution. This isn't a class in probability per se, so we're not going to delve deeply into how this distribution is used and why it's one of the important ones. It's actually a generalization of the exponential distribution, so that and one of the nice things about it is it has a variety of different shapes that it can have. So if you look at the PDF, which is a nice way of kind of describing behavior. So if k is less than 1, then the PDF actually has kind of a really big infinite spike at the origin. So again, this is the PDF, not the CDF. So for k less than 1, there's an asymptote at the origin. The PDF looks like this. If k is equal to 1, it's actually an exponential. Again, these are the PDFs, and if k is bigger than 1, it actually looks something like this. Badly drawn, but so here, depending on what these are. So these are, k is called the shape parameter. And And lambda is called the scale parameter. So basically, the K is what determines roughly how this goes. What the basic properties of it are. That is, if K is less than 1, then actually just a huge number of the there's a tremendous amount of probability right near the origin. I haven't drawn this quite to scale. It actually takes a huge dip, and most of the probability, most of the variables will be like down here. We'll see this when we start generating them. Again, in exponential, it's kind of similar, where most of the variates are kind of down toward the origin. But once we get bigger than 1, then the majority of the probability is in this hump here. And it can look kind of normal-like, or it can be kind of skewed. It all kind of depends. So this is a very useful distribution because it can take on all of these different shapes, and there are particular situations where this is a useful distribution to use. And again, we won't be getting into that, but our purpose here is we want to generate from this. And it just so happens that this has a cumulative distribution function that is invertible, so we can actually stand a chance of doing it. So let's see how that would go. So in order to find what we want to do is we find the inverse. We want to find the inverse, the functional inverse. And so to do that, we set a parameter like this, and this is for u between 0 and 1. And those are the values that will be generated by a uniform 0-1 distribution. So you always start with this expression, and then you plug in what the value is. And now it's just a matter of algebra. So what we want to do is we want to solve for x. Okay, so let's see what we can do with this. Well, once we want to put the whole e thing on one side. So if we bring the e over and bring the u back to the other side, we get e to the minus x over lambda to the k is equal to 1 minus u. Okay, just algebra. Now we can take the log of both sides, the log of both sides, and the log cancels the e. We can't forget the negative because that would really screw things up when we start to try to generate them. That's supposed to be a log. All right, and now we just start unraveling. Minus log 1 minus u. And again, just as a check, because the log of a number that's less than 1 but bigger than 0 is always negative. So negative and negative is a positive. And so we can take the k through. We need to verify that. So x over lambda is minus log 1 minus u to the 1 over k. So again, we don't know what k is. K can be any value bigger than 0. And likewise, lambda can be any value bigger than 0. And then finally, x is equal to lambda minus log 1 minus u all to the 1 over k. And that's our inverse as a function of u. And this, in a way, is what shows that lambda is a scale parameter. So we see that lambda basically multiplies this whole thing. So, you know, if lambda gets big, then that's going to just make things bigger. And if lambda is smaller, then it's just going to make them smaller, but it's not going to affect the shape. But K is going to affect the shape because we have it here. Okay, so this is, so our method now is generate U, uniform 0, 1. Oops. And then we return, it's not letting me do it. I'll do it on a new page. So what we do is we generate, this is the method. And when you say this squiggle, that means we generate this as a, following this distribution, and then we return minus lambda, I'm sorry, not minus. We return lambda times minus log of 1 minus U, capital U, to the 1 over K. Keeping in mind that in Java, ln is depicted as log for a variety of reasons. Okay, so that's how you go about doing it. In other words, what you do is you find the CDF and then you try to unravel it and solve for X. Okay, any questions about that so far? And then just to kind of drive this to completion on this, let's see, let's take a look at how we might do that. And if you do a pull on the code, I've actually implemented this Weibull variant. And even commented it. So here's the, you know, here's the essence of what I just did. Okay, so here's my U. I made it lowercase here. You can make it uppercase. Doesn't really matter. Java likes lowercase variables. In this particular context, calling it sort of U is not the worst thing in the world. Usually when we're writing code, we want our variables to be a little more descriptive. Here, that's descriptive enough in this. But then notice that in defining our variables, like the shape variable K, I called shape, and lambda, the scale parameter, I called scale. So there the variables are descriptive. And then the java.comments, for example, on the shape, describes what the different values are. And we'll actually see that a little bit. Okay, so this is our lambda. So here's our expression. We have 1 minus U, the log of that. Again, ln, keep in mind that ln is log here. And then Java has this method called pow, which is how you take the power of something. So the power of this to 1 over the shape, which is the 1 over K. So that's the expression that we had before. Everything else is just all the setup for how to get the random variate factory to work with this. See, what the random variate factory does is it actually calls the set parameters method, and it passes in the arguments that you give it. And since the different random variables have different types of parameters, that is, there are some random variables for which the parameters might be an integer. There are other random variables for which the parameters are actually arrays of things. Again, we won't get into that a lot. If you're ever interested in that, those are useful things depending on what the context is. So the idea is that these, because they're objects, we don't know coming in, we can't guarantee that they're actually going to be numbers, and we can't guarantee that they're going to be enough of them or the exact right amount. So first we say, have you given me 2 parameters? Because I need a shape and a scale. One option you could have here is you could say, well, you always need a shape parameter, but the scale parameter could be 1 if you don't give one. Again, that's something that we could possibly do if you wanted. Here, we're just going to be very strict. You have to tell me both the scale and the shape. And in fact, they have to be in this order. They have to be shape and then scale. And then all of that is basically there. So here's how we are going to test it out. So what we do is, again, notice that the convention is that if you say variate, then that's something that the random variate factory kind of understands. It actually is not necessary, but it's something which is strongly encouraged. So if I see something, so here was our right triangle variate from yesterday. Here's the Weibull variate that I just wrote here. And if I just say Weibull but leave variate out, then the random variate factory is good enough for that. Now here, just to kind of illustrate, so what I've done here is I'm getting an instance with a shape parameter of 5 and a scale parameter of 1. I'm going to keep the scale parameter as 1 just for this purpose. And just as we did yesterday, I'm going to generate 1 million of them and write them to a file. And so all this code is just basically exactly the same as it was yesterday. We're just creating this file, writing to it with a buffered writer from a file writer, etc. So if I run that, then okay. So what was printed on the console was just this print line here, just to verify that the right things got in. See, here's the thing. Notice that here I said number, not double, even though I'm using doubles. See, you have to be a little careful. So for example, here, I gave the shape parameter as an integer. If I were to cast this as a double, which I could, I'm now going to get an error. At least I should get an error. Yeah. See, look, it says integer cannot be cast to a double. See, the integer, if you remember, that an integer is not compatible with a double in the object world. So that is why I said is a number. So if a number, an integer is a number, and every number can be, I can extract the double value for. That's what we have.
What did you just do to correct that? You like right-clicked and.
Oh, right here. Okay, you see this little blue stuff? See, it says line change. I just sort of clicked on that, and then I can just selectively undo anything that I have there.
Oh, okay. You've probably been doing that all year, but I never noticed.
Yeah. Okay, so now let's see if this is the file, and it's got 1 million of these things in it. And okay, now yesterday I was using the R package, but you all said that you use jump. So I installed jump, and so we'll use jump for this. So now this was actually, it was kind of nice, but I wasn't as impressed with this with the graphics, as we'll see. So in order to do something like this in JMP, we import a text file, and here, here's my Weibull. This is what I just generated. And then, let's see, it did its best guess. It said fixed width, that's okay. If it were like a CSV file, then we need to worry about that, but this seems to work okay. I assume you can all see this, right? And so I just import that, and then it imports it into a data set. And now with this data set, I can analyze the distribution. I'll just do the histogram only. So I just drag this over and I hit OK. And then it creates my distribution. And then for some reason, they kind of do them vertically, and I can set it to horizontal. So we see for here, K was equal to 5. So the shape parameter was 5. And as I said, it's a unimodal distribution that looks something like this. So let's say, let's change it to 1. Remember, he said that 1 was the same as an exponential. So now I want to be looking at something that is quite similar to an exponential. So it's not going to look like this. It's going to be all tilted with this with a maximum on the left side. So let's we can actually let's see, where is the thing? Oops, I want to jump home. Let's open. Let's see if it'll let me just kind of open it. Oops, where'd it go? Okay, so there's the Weibull 1 and 1. That's what I wanted. And let's analyze this. And again, if we kind of, I don't know why my biggest complaint about JMP so far is the way they do these. Their graphs are always vertical. I don't know why. Okay, so we can see that it's really skewed to the left here. So starting at 0, and this does have some very cool things. So like if you click on one of these bars, it will show you in the data which ones were associated with that. So that's a nice feature. Okay, so now let's have a shape parameter that's less than 1 and see what that does. Oops, I didn't want that. And so now with the shape parameter less than 1, here's Weibull again. Okay, so here's this, and for some reason also. Okay, so again, let's analyze the distribution. Just the histogram, please. And then, as we can see the spike at 0. Remember, theoretically, this spike at 0 is very, very big. And notice it has a lot of actually see the N. So out of 1 million has like almost 631,000 observations in that first spike. So that's, and if we go down even more, so let's say to 0.5, then let's open it again. Okay, so there's that, and then let's analyze that same way, histograms only. And then, okay, we see in this that here there are about 900, almost, wait, 892,000 out of 1 million observations are in that first between 0 and whatever that is. And in the next one, there are just, I can't even get to it here. So there are only like 65,000 in the next one. So that's indicative of the fact that there's this huge spike at the origin for the Weibull. Okay, so that's so what we've done, we've gone all the way from the CDF for the Weibull to the inverse transform method, and then all the way to the implementation. Okay, any questions about this? And again, it was requested that I do an example, and that was the example. So let's, we can.
Arnie, for our homework this week, though, you just want us to do to write out the math, right?
Correct.
Okay. So
for now.
For now, yes. I know it always builds. But so what we just did in the first part of this problem, that's the only thing you're requesting of us.
Exactly. Yes.
Solve for X.
Yeah.
Okay.
I don't need all that. No. Come on. All right. Now, okay, so that's the inverse transform method. Now, I did want to give you a peek into at least one other one. As I said, there's a third general method called inverse transform that we're not going to deal with, but regardless, just know that it's there. I'm not going to make you responsible for it. But the composition method is a way of taking a complicated problem, a complicated probability distribution, and breaking it down into simpler ones. Okay, so the idea is that if we can write our CDF as the weighted sum of other CDFs. So each of these are CDFs, and these probabilities, these are all probabilities. So the sum of these probabilities are going to be equal to 1. In other words, what these P's represent is a discrete probability distribution over the integer values 0 to n-1, and we're using the zero-based indexing. Okay, so in other words, this is a weighted sum, but the weights are all probabilities. So the idea is that now, instead of, well, we assume that we can generate from each of these because they're kind of simpler. So now what we do is we need 2 random variables. So first we generate a random index I. So this is basically a random index. A random index. And then what we do is we just generate from that CDF that we've picked out with that random index. Typically, this is how we can build up more complex distributions using our building blocks. And the building blocks are almost always inverse transform methods. So the inverse transform method, you know, that we have, and hopefully now, you know, with some of these examples and showing the PDFs, the histograms that get generated from that, hopefully that should be giving you a sense that this actually is doing what it claims. Again, the math, well, my experience is the math rarely convinces anyone, which is why it's important to actually generate them, look at the histogram and see that it's the right shape. We could go even further and we could apply statistical tests to the data that's generated and see whether or not it passes the statistics test that said this indeed was, say, a Weibull distribution with those parameters. We're not going to go there, but in a serious study, that's something, of course, that you would want to do. But at the very least, the most convincing thing is you generate a pile of them, you look at the histogram, is it the right shape? That should give you confidence in moving forward. And to dot all the I's, of course, you would want to do the statistics. I don't want to say you should skip over that, but looking at the histogram is a key element to that. Okay, so why worry about this? So let's look at the general triangle distribution. Okay, yesterday, or was it the day before, we've looked at two different triangle distributions. We've looked at one that looks like this, and we've looked at one that looks like this. But the most general one, actually, most general triangle actually looks something like this. Now, the functional form of the general triangle is simple enough so that we can use the inverse transform method. And in the reading, I believe that there is an inverse transform method that is shown for that. But given what we've already done, in other words, we already have the right triangle and the left triangle, but these in and of themselves cannot generate anything that looks like this. They can't. But if we put them together, and in other words, this is an extension of the virtue of laziness. In other words, instead of kind of working out everything that we had already, instead of working out something totally new, let's use what we already have. We have this piece and we have this piece, just with a little bit of extra, stuff. In other words, we had, technically they were this, but it turns out that if I have a random variable x, if I do something like this, so let's look at let's look at this one. So here I have A to C, and here I know how to do 0 to B. So how can I, if I have an X that gives me 0 to B, how can I turn that into, or let's say I have one that goes from 0 to 1, for example. Let's take B equal 1, and then turn it into one of these guys. Well, what I can do is my B is equal to C minus A. And then I want it shifted over by A. So this is what will give me this, if X is one of these. And similarly over here, if my, let's say if I have a Y that's one of these, from -1 to 0, then B minus well, actually B what's it? B plus B minus C times Y will give me the same sort of thing. Okay, so now all I need to do is figure out what these probabilities are. And actually, I just need to figure out what this probability is. And that's fairly straightforward. So let's see what that looks like. Let's get rid of all this nonsense here. So let's erase that and just sort of see what's going on. Okay, so our total PDF is this dark line here. So the area, what's the area under that curve? It has to be 1. That's what a PDF is. And so because of that, now the base of this triangle is B minus A. And so what that means is that the height of this triangle has to be 2 over B minus A. Right? Otherwise, that's the only value that will give us a height of an area of 1. And so P0 is going to be the area of this triangle, just this piece right here. So what is that area? Well, it's 1/2 the base times the height. So P0 is, oops. On. Let me pick a different color here. All right, so P0 is 1/2 the base times the height. The base is C minus A. The height is 2 over B minus A. And so that gives us C minus A over B minus A. And P1 is just 1 minus that. Okay, so now we have all the pieces in place. We know how to generate from this triangle. We know how to generate from the triangle on the right. And we now have our weight, our probability. Okay, so here's basically what I just did. So we want to find P0 and P1. The height is 2 over B minus A. So P0 is the calculation I just did. And just for completeness, P1 is just 1 minus that. And then it turns out to be this quantity. Okay, so here's how this works. So to generate the left triangle, we have A plus C minus A times root U. Remember that was kind of what we had before. Now, to generate, because that's going to be between A and C. For the right triangle, we had this piece, which was from C to A. I'm sorry, C to B. And so this is what we would do for that. Oh, what happened to the slide that had the method? So let's, I guess I better do that. So here's what we, all right. Okay, so here's our method. We want to generate U and a V, 2 of them, independent, uniform, 0, 1. And there's a missing slide that that lists this. So I'll put this in the I'll add it and upload the, okay, so now if, here's the thing, if V is less than P, 0, which was C minus A over B minus A, we return A plus C minus A times the square root of U. Else, see, this is why we didn't really need to compute B1. Else, we return B minus B minus C times the square root of 1 minus U, because that's what we had there. So this is our method. Using composition. Okay, so now to that end, we have a triangle variate that uses composition. And this is, again, this has been pushed there. So there are 3 parameters. I want the left, the right, and the center. Those are the 3 values there. So here's how to implement that method that I just gave. So here's, remember I said V and U. So first generate V and U. And again, how do we generate uniform 0-1s? We take our random number generator and we call draw. Okay, this was, okay, remember, we used V to choose which, whether we went on the left one or the right one. And we did that with this probability. And that it was, remember, it was C minus A over B minus A. So that would be the center minus the left over the right minus the left. And this is A plus C minus A times the square root of U. Else, so now if it's not less than this quantity, we take the right minus the center times the square root of 1 minus U. Okay, so now it's not at all obvious what this is going to look like, which is why it's important to test it out. And what I'll test my triangle. The reason I say my triangle is because there's actually one of these in SimKit. So I wanted to make sure I use this one and not the one that's in SimKit. In fact, just to double verify that. I'm going to print out the name as well. The other thing, what I did here was that this is to illustrate the importance of using, again, using numbers here rather than doubles. So notice here, the 3 is actually a float, not a double. And I usually don't use 5L is a long and 2 is an int. So I'm giving it a float, a long, and an int. But when I run it, I actually want doubles. Okay, so the 2-string, I said triangle using composition, and notice that it took these values and turned them into the right ones. And then this is just verifying that this is mine and not the one in SimKit. Okay, so what that created was that created the triangle composition one. So let's go back to our friend Jump. And import that file. So this is the triangle with composition. And okay, so it was using fixed width fields. Let's really want delimited fields instead. No commas there. Okay, so it pulled them all in, got all 1,000,000 of them. Let's analyze the distribution. Well, actually, I'm gonna analyze the whole thing here. Let's leave that. We'll do okay, and it gives us the moments as well. So let's turn this right side up just to kind of take a look at it. All right, so again, this is a teeny little little graph, but I think it's clear enough that first of all, we see the triangle shape, and we can also see in the summary statistics, we see the maximum is like 4.99 blah blah blah. So that means that remember, our maximum value was 5, our minimum value was 2. And so the minimum generated value was like 2.001 something. Okay, so that, and then our mode was around 3. And we see that kind of right around 3. And if we take a look at the values from this that are shaded, so 3.06, 3.03, all the shaded ones are right around 3, and that's where the mode was. That was this 3 here. Okay, so what this demonstrates is that we were actually generating from the right distribution. And hopefully this and again, let's look at the let's look at the way that it was done. We generated 2 uniform guys, and then we said, okay, if this first uniform guy is less than this quantity right here, we're going to generate one of these triangles that was kind of on the left. And if it's not, we'll generate one from the right. And it's not at all clear. Again, if you were to read this code somewhere and say, what is this going to do? What kind of probability distribution? What's if I were to generate a bunch of these and collect, estimate, create a histogram of these, what would that look like? It's not at all. I guarantee you that most of you, and certainly not me, would be able to tell that the shape is going to be this triangle. The only way that I would be able to do it is the fact that I know that that's the case. But if I didn't know that was the case, I would never in a million years guess that that's what the shape would be. And yet that's what it is. Okay, so let's go back to our, okay, so that's, okay, then just as a, just for completeness, kind of what's going on in SimKit was this. We had this random variate interface. And what the interface specifies are these 5 methods. The main one, of course, the most important one is the generate method. In other words, every random variate, every class that implements random variate has got a generate method. And so if you call that generate method, it will just go and grab the next one. The set and get parameters, especially the set parameters, that's something that the random variate factory uses. Because remember, when we call with a get instance, we give it the name and then we give it a bunch of values after that. What the random variate factory does is it takes those values and it calls set parameters with that. That's how we were able to do that. The get parameters is just for completion. But then what it does is it calls set random number using its default random number generator. So that's that, again, this is something that we never call. But that's the interface. Now the random variate base simply implements the 2 random number methods together with a protected random number instance. So that's just because every time you do this, you either have to kind of write these, or by simply subclassing random variate base, then we don't have to keep writing the same things. But every distribution is going to have a different number of parameters. So here are the 3 parameters that we had. They just had getters and setters. But then the 3 methods that were not implemented by random variate base have to be implemented here for this to be a concrete class. So we implemented the set parameters. Get parameters is always very straightforward, but then generate is sort of the main object of this. So this is where we would implement the particular random number algorithm that we're using for that particular distribution.